Okay, we are now recording, just so that everybody knows. The goal is to go through a few bits of the 2C project and a little bit into 2Z if there's time. The goal is to make it so that even if you haven't even read the specs yet, you'll be able to come out of this with an idea of how you're going to be starting this. So I guess let's just get into it. So 2C is the 2C, you're going to be writing an LC2K program that computes the combination formula. So that's like C of nk, where you have a list of n items and you want to see how many combinations of size k you can get from them. And the property that they're leaning into here is that C of nk is equal to C of n minus 1k plus C of n minus 1 k minus 1. So this is a lot like, this can be represented with Pascal's triangle, which is what I've written over here to the right. In Pascal's triangle, you get a space by adding the two spaces above it. So, like, honestly, save an image or save anything of a Pascal's triangle so that you can reference it while you are testing your programs, that you are making sure that you're getting the right numbers. That's really, this is really important. So Pascal's triangle is going to help you conceptualize what's actually going on each time and how you're going to be branching from like 3 to 1 and this kind of thing. I think that's basically it for, so does everybody understand how combinations work? Like we took 2 or 3, kind of. That's not going in the recording. You're going to you're going to be giving n and k. So on the Pascal's triangle, it's going to look like this is maybe the 5th, n equals 5. So n equals 5 puts us here. And then we're going to say r equals 3. That's another n. There we go. R equals 3 is going to put us 1, 2, 3 at 20. I went down to 1 too far. My bad. 1, 2, 3, 10. So you're going to start here. You're going to compute 4 combination 2 and 4 combination 3. In order to compute each of those, you're going to have to compute the 2 above it. And in order to compute each of those, you're going to have to compute 2 above it until you reach a 1. And that is your base case. And that's where you're just going to return 1. So that's the overall kind of like abstract concept of what you're going to be programming here in LC2K. Combination, you're going to be making a program that returns the sum of, I think I wrote this somewhere, literally right here. You're just going to be computing a program that runs itself twice and then adds the 2 answers together. So over here, I've got a structure that you should follow in order to, and I say should because it's like, you know, a pretty strict structure for what you're going to be actually computing in LC2K. So the first thing you want to do at all is to check if r is equal to n or r is equal to 0. That's just 2 really quick BEQs. And if either of them are true, then you just skip to like the very end and set register 3 to 1 and return from the program. I'm going to try not to write any actual LC2K code on here, but you're going to want to use $. To get back, by the end of your program, 7 will be the return address to go back to whichever function called this function. So to return, it's just $7, and then you want to put some register here. It doesn't matter. You don't need, because $. Saves the next line of code, the address of the next line of code into a register. But when you're returning from the function, you're not going to need that information, so you just put it into any register that isn't important, which is usually 4 or 6 because they're temporary variables. So that's how you return from a function. And if you're the base case, r equals n, r equals 0, then you're going to set r3 to 1 and return. Otherwise, you're going to want to do some register storing. Yay, let's use the stack. This part's so much fun, trust me. So this is going to be using a lot of register 5. Register 5 is your stack pointer. It points to the next available space in stack. So the next time you want to store something to stack, you're going to, like say, memory at stack plus R5 equals whichever register. you're going to be doing that. And then I mentioned this on the next page. Yeah, so this is when you're using the stack. So you set a memory register 5 plus stack to whichever register, and then you increment 5, saying that the next available space in the stack is 1 further. Then whenever you're retrieving from the stack, which we'll get into later when you'll actually use this, you're going to want to decrement first, and then retrieve, and then just use LW to retrieve it from the end of the stack. So for the call stores, you're going to want to store any call saved registers at the very beginning of your program after the base case. So this is at least going to be R1, R2, and R7, because those will need to be saved for when you return back to the previous program. You could also store like R4 and R6 if you really needed to, but that depends on your implementation. These are the 3 big ones you need to store, and do not store 5, please. You don't need to. Once you're done with that, you're going to call the function again after you have decremented n. So n is in register 1. You're going to want to decrement that, and then just load the address of the beginning of the program into whatever register, like 4 or 6, because those are your temporary variables, and then jump to that. And you don't want, this is a big thing that I've heard a lot of people are confused about, trying to think about the whole program as like a series of all states in the entire thing, trying to compute the entire combination in one go in like their head. You want to think of this as just one function that only does these 9 things. You don't want to think of it as like actually computing the combination, because your brain will try to do that, and it gets very angry, and it gets very tired very quick. So if I'm making any sense, think of this as a single function doing its one thing, and whenever you make a function call, you can trust that it will get you the correct answer, no matter what. You don't have to worry about how it gets it at all. Think about one function at a time. So once you have jumped to the function, it will return for you. And in register 3, magically, you will have the combination, which would be, I should probably write somewhere here. So we'll do it here. C of n minus 1. Okay.
Can I ask a quick question?
Go ahead.
So, like, I haven't started, so I'm just getting.
I'm going very fast. So
yeah, no, but you mentioned that for stage 3, we would be making the function call. Do we decrement register 1 inside of that function call, or is that something that happens after you return from function call? You're
going to want to decrement register 1 before you jump to the start of the function.
Okay.
It's essentially just, n minus equals 1, or n minus minus. I'm in Python syntax right now. So, I guess that's more clear. So you're going to want to do that beforehand, so that the value that you're putting into the function the second time is going to be n minus 1.
All right, thanks.
Yep, you got it. I'm not sure what my pace is right now, so if you do have questions, please ask. So the next thing is a bit tricky. This is kind of interesting. You need to save the results of your first function call, this answer right here, as a caller stored register, because it's going to be overwritten when you make the second call, because it also has to return in register 3. So you should, there are a few different ways to implement this. One way you can just do what we did up here with the call stores and just save it to stack, and that's using the memory R5 plus stack equals register A, and then increment register 5, sorry. There are other ways to do it. That's probably just the safest way. Then you're gonna make the function call for a second time. This is going to be exactly the same as stage 3, except now instead of decrementing n, which is R1, you're going to be decrementing R, which is in register 2. So this is going to get really messy really quick, and that's fine. Sorry, it's not R, that's K. When I was programming this in my notes, I kept on switching between using R and K for these for the second argument in the combination. So that's my bad if I accidentally say one instead of the other. I'm going to try to stay consistent with K. So you're going to decrement K and then jump to the start of the function again exactly as you did in stage 3. Then you need to load the result that you got from call 1. And this doesn't have to be back into register 3. Normally when you're doing a load and save pair, you're going to want to load and save it into the same register. But that's not really necessary for this program because you don't want to overwrite your function call or your results from function call 2, which is in register 3. So you can retrieve it into any register, and then you just add that to the result that is already in 3 and save that into register 3. That is now your return value, and that is what you want to give back to the function that called your program. Then you want to do the caller loads. Definitely think of these as an exact mirror of your callee stores. It should be the same number of lines, unless you need to load 1 or -1. But that doesn't matter. So it should be the same number of lines. You want to decrement first, and you need to do it in the opposite order for how you stored them. So if you stored register 1, and then register 2, and then register 7, so this is our LWs, then you're going to want to, these are our SWs. Then you're going to want to load register 7, then register 2, then register 1. So it's going to be exactly mirrored from how you stored them. And you can rest assured that by the end, your register 5 increments and decrements will have canceled out, and you will come out of this function with the exact same register 5 value that you went in with. Then you're just going to be returning the sum. This is just a Joller command real quick, like we pointed out down here, in order to jump back to the program that called it.
Right.
Yes.
I have a question.
Please ask.
So can you go back to the previous slide? So I understand the first function call, that's n-1, combination n-1 and then k.
Yep.
So what's the reason why in the second function call you only decrement k? Because if n is already decremented all the way down for the first function call, and if it is restored, then shouldn't you be decrementing n in the second function call as well?
You will be decrementing n before you call the function. So right here, you're on line, I don't know, we're going to say this is line, I'm just moving to this page because there's more room.
Okay.
Line 8 or whatever, and you decrement n. And then line 9, you call C of n, which is now n-1, nk. Then when you return, n will still be 1 less than what you started with. It will store this C right here will store n-1, and then it will bring back n-1 at the end. So when you make the second call, you just want to decrement k so that this, I'll draw arrows to help this in a new color. Let's do green. It's going to be Christmassy. So this one on the top is C of n-1k. And this one still has n decremented, but we've also now decremented k.
So the first recursive call doesn't technically complete until you've...
First recursive call absolutely has completed. It is entirely done. We don't need to worry about how it did it, but it is done.
I guess I'm confused then, because if the first recursive call is completely done, then n is already at its base case. So then by the time we start our second function call, n is no longer the n-1, isn't it? Technically 1, but based on this diagram, it seems like you're doing one call for C1 and then one call for C2.
I understand what you're saying. I think I understand what you're saying. Essentially, you don't need to worry about what goes on inside this. inside this
All
function
right.
call. It's totally
Okay.
fine, because if you try to think about it, it's going to overcomplicate your thinking process, and brains aren't made for that. That's what computers are for. So you're going to come out of this C of nk with register 1 still being the same, register 2 still being the same, register 3 having the value that you need, and register 7 also still being the same.
So just recursive leap of faith.
Yep, exactly. Recursively,
All right,
you can
dope.
trust that. You can trust that function to do what you need it to do.
All right,
and that's
sounds good.
cool. And that's because you're doing everything correctly in your stage 2 and your stage 7 and your stages 4 and 6. As long as you do everything correctly in, like, think of it as your first rendition of this function, then it'll go perfectly fine for every other one. Like in C, or Python, or C++, or whatever's your fancy. So does that all make sense?
Thank you.
Okay. That was a very affirmative yes. Over here, I just have notes, like the registers that they give us in the specs, what they expect for each register. Value 0, register 0 is obviously going to be value 0. You can't change that. Register 1 will contain n, 2 will contain k. Yeah, there's the inconsistency right there. 5 will contain your stack pointer, the next available space in the stack, and 7 is your return address. And 4 and 6 are your extra variables that you could use for kind of anything. They recommend using 6 to hold your constants, which could be 1 or -1 or 42 or whatever number. And then they say you should use 4 for like more dynamic variables. Okay, I said dynamic. I know some of you just came out of 281. I'm sorry. I didn't mean to cause any trauma. I think that's the majority of the notes that I have for 2C. Just off of...
I have a quick question.
Go for it.
So like on the other page, like when you were talking about like when we use JLAR to like jump to the like function return, like is that what causes the, like, that's not what causes the recursion. Like at line 8, that's like going back to the function that like originally called it, right? If that makes sense. Like what is line 8 doing?
Line 8 is just your return x.
Okay, it's returning to like the like combination main.
Yeah, the function that called it. Yeah, is what it's returning to. It is. It is wonky because we're using Joller for two things, so I get why you're confused. Go ahead. Okay,
and then the other JLAR is like for call 1 and call 2, you're going back to just the combination function that we're making, right?
For these, for these two Jollers, you're going to be, these are equivalent to, if C is our program, you know, like, whoops, I'm writing in Python syntax again. So C is our function, then these two are equivalent to C of nk. I'm going to write this on like another page real quick. I'm going to make sure I say this correctly so it's not too confusing. If you are doing a Joller 7, then that means that you are returning to the function that called it, because 7 contains the return address. So this is equivalent to return and then whatever variable you're returning, which would be our sum. If you're doing Joller to something else, which is usually 4 or 6, because those are our available variables, then that's equivalent to calling C of nk.
Okay, that makes sense. Thank you.
Mm-hmm. And then before you call this function right here, or this instruction, you're going to have a load word instruction that will put the address of the beginning of the function into whichever register you're putting here.
Okay. Okay, that makes sense.
Okay.
Okay.
So I think that's C address, LW0, and then whichever register C address is the one that they want you to use, because that's the beginning of the program. Okay. Are there any other questions? Even if it's not like a burning question, just like maybe a simmering question.
So when we're when we go to retrieve the call you saved registers for like line 7, are we retrieving and restoring call 1 or call 2 in this case?
We are actually, yep, that's a good question. Line 7 is connected to line 2.
Okay.
So these two are like your, I don't know, you could think of them like brackets for your program or something like that.
Okay.
These are just going to be the first thing and last thing that you do in your program, aside from the base case in this situation. The caller store and load. So the caller is connected to is like bracketing function call 2. The reason for that is because we don't really need to store anything over function call 1 that it won't already store for us. But function call 2 will overwrite our previous value of register 3, which we really need to keep. So we're turning register 3 into a caller stored register, but only for function call 2. And then we'll load it back when we're done. So each of these are stages that are kind of going to be like roughly what you'll write in your program. They should be like half a dozen lines long, 6 or 7 or so each, and some of them are just one line. I don't know where I'm going to go with that, but that's about what your program will look like in the end. 6 lines for each of these stages. I don't want to move on to 2Z until people feel like comfortable with 2C, although 2Z is mainly just theory about combinations and how to compute them a bit faster. Please do 2Z. Once you have 2C done, you can just like modify it a little bit, and then you get the extra credit points. So please do 2Z.
Right, not all of us are at your level.
The requirement for 2Z is to make your program run C of 14.7 in less than like 110,000 instructions. And the first time you make this program, your program's going to run about like 130 roughly instructions. So you make a quick little cut, and it quickly cuts it down.
We will cross that bridge when we get there. Let's finish
okay.
2C first.
Let's go for it. I'm glad you're saying that.
Yeah, I want to get the actual project done first.
Yes. All right. I'm going to think of what tried to cause me trouble when I was programming this. Just going to reiterate. Definitely think of this as a single function doing a single thing, and not as the whole tree that you would make when you're drawing this on Pascal's triangle, because that alone is hard to draw, let alone program. So this is one function doing one thing, and that thing is calling itself twice and returning the sum. All right, I think I've said everything currently on the slides. Is anybody really confused somewhere or in general? Because I definitely went faster than I expected I would.
I have a quick thing. So with like the stack, is that like already going to be set to like, do we have to set the stack in our program?
Good question. You do not have to set the stack. In 2L, you set the stack to be the last line, the first like available line in your program. M plus N, I think we kept on calling it. So that was, yeah.
It already does it for us. Okay, cool.
Right. In fact, I think if you define stack, it's going to complain to you and say, hey, that's not allowed, that's illegal. So you don't have to worry about stack. It's just a memory address that you can use for storing all of your registers. Or storing other stuff if you feel like breaking the rules. Don't do that. Don't do that, please. Sorry. Only store the registers.